There are numbers running the universe, not metaphors. Actual numbers. Physical constants. Quantities baked into the fabric of reality that determine how strongly gravity pulls, how tightly atomic nuclei hold together, and how fast light travels through a vacuum. And those numbers are precise, not roughly precise, not approximately correct, precise to dozens of decimal places. And if they were different, if any one of them shifted even slightly in either direction, you wouldn't be here. I wouldn't be here. Stars wouldn't exist. Atoms wouldn't hold together. The universe would be a cold, structureless, featureless, dark nothing. Here is the number that should make you stop. The cosmological constant, the energy density of empty space, the quantity that drives the accelerating expansion of the universe, is fine-tuned to within 1 part in 10 to the power of 120. That's a decimal point, followed by 119 zeros, followed by a 1. The physicist Roger Penrose called it the most jaw-dropping fine-tuning in all of known physics. For comparison, there are estimated to be around 10 to the 80 atoms in the entire observable universe. So the precision required for the cosmological constant to sit where it does is more exact than picking a single specific atom, at random, from everything we can observe, twice over. And that is just one constant. This is called the fine-tuning problem. It is one of the deepest, most genuinely unresolved questions in all of science. And the answers that have been proposed, every single one of them, raise harder questions than the problem they were trying to solve. Before we go further, we need to establish what we're actually talking about. Because physical constants is a phrase that can slide past you without landing. Physics runs on numbers that don't change, not with location, not with time, not with the observer. They are fixed into the structure of reality as far as any experiment has ever shown. The gravitational constant tells matter how hard to attract other matter across a given distance. The speed of light sets an absolute ceiling on how fast anything can move or any signal can travel. The fine structure constant, a dimensionless number close to 1 over 137, governs how strongly the electromagnetic force acts on charged particles. These aren't incidental details. They are the operating parameters of reality. Martin Rees, the British Astronomer Royal, identified 6 of them as especially critical in his book, Just 6 Numbers. Change any one, he argued, and the universe becomes not just inhospitable to life, but incapable of producing complexity of any kind. No atoms, no chemistry, no structure, just an undifferentiated, expanding medium, and nothing more. Consider gravity first. Gravity is extraordinarily weak compared to the other fundamental forces. This surprises people. Gravity feels significant because the Earth is very large. But on the scale of particles, gravity is essentially negligible compared to electromagnetism. A small fridge magnet can overcome the gravitational pull of an entire planet to hold a piece of paper to a wall. Electromagnetism is roughly 10 to the 36 times stronger than gravity. And this weakness is not a flaw. It is a condition for life. If gravity were even a modest fraction stronger relative to the other forces, stars would burn through their nuclear fuel catastrophically fast. Measured not in billions of years, but in millions or thousands. Planets would have no time to cool, no time to develop complex chemistry, no time to produce anything capable of self-replication. Life requires patience on cosmic timescales. Stronger gravity removes that patience entirely. If gravity were weaker, gas clouds would fail to collapse into stars at all. The temperature and pressure required to trigger nuclear fusion would never be reached. The universe would remain a diffuse, slowly thinning fog of hydrogen and helium, dark and unchanging, forever. The window in which gravity produces stable, long-burning stars, stars like the sun, which can warm a planet for 4 billion years without exploding or burning out, is remarkably narrow. Now, consider the strong nuclear force. This is the force that holds atomic nuclei together. Protons carry positive electrical charge, and positive charges repel each other. Electromagnetically, the nucleus of any atom should blow itself apart instantly. The strong nuclear force overrides that repulsion, binding protons and neutrons together at very short ranges. If the strong force were a few percent stronger, hydrogen, the simplest element, just one proton, would fuse with itself almost instantly after the Big Bang. There would be no hydrogen left in the universe. And without hydrogen, there are no stars, no water, no organic chemistry. If it were a few percent weaker, nuclei with more than one proton wouldn't hold together at all. You'd have a universe of solitary hydrogen atoms and nothing more. No carbon, no oxygen, no iron, a few percent, in either direction. That is the margin that separates everything from nothing. Of all the coincidences in this story, the one surrounding carbon is the one that shook the scientists who found it most deeply. In 1952, the astronomer Fred Hoyle was working on the problem of stellar nucleosynthesis, how stars forge the elements heavier than hydrogen and helium. He knew that carbon was abundant in the universe. He knew it was the backbone of all known life, and he knew it was produced inside stars through a process called the triple alpha reaction, in which 3 helium-4 nuclei fuse together to form carbon-12. The problem is that this fusion happens in 2 steps. First, 2 helium nuclei collide to form beryllium-8, but beryllium-8 is almost catastrophically unstable. It exists for roughly 10 to the minus 16 seconds before falling apart again. The window for a third helium nucleus to arrive and fuse with it before it disintegrates is vanishingly small. For carbon to form in stellar interiors in the quantities we observe, for carbon to be as common as it is, quantum mechanics had to provide a resonance, a specific energy level in the carbon-12 nucleus that dramatically increases the probability of the fusion completing before beryllium-8 decays. Hoyle calculated what that energy level had to be, approximately 7.65 million electron volts. Nobody had measured it yet. He went to a laboratory at Caltech and asked the nuclear physicists there to look for it. They were skeptical. They looked anyway, and the resonance was exactly there, at 7.656 million electron volts. Hoyle had predicted an undiscovered feature of nuclear physics from the fact that carbon exists. He reasoned backward from abundance to necessity, and the universe confirmed his calculation. He was, by all accounts, unsettled by this. Hoyle was not a religious man. He was one of the most rigorous and iconoclastic cosmologists of the 20th century. The same man who coined the term Big Bang as a dismissal, who spent decades challenging the consensus view of cosmic origins. He did not reach for comfortable explanations. But this result troubled him in a way that never fully resolved. He wrote later that the idea of a blind force producing such a coincidence was deeply difficult to accept, that some organizing principle seemed to be at work in the numbers. Most physicists today would frame it differently, but they wouldn't dismiss the discomfort. Because Hoyle's carbon resonance remains, to this day, one of the most striking examples of apparent fine-tuning in all of nuclear physics. And no one has fully explained why the resonance sits exactly where it needs to. Let's pause the physics for a moment, because numbers like 1 part in 10 to the 120 are technically precise and experientially meaningless. The human brain did not evolve to feel the difference between 10 to the 80 and 10 to the 120. Both are just incomprehensibly large. So let's try something else. Imagine you are an engineer. Your task is to design a universe from scratch. Not this universe, just some universe. You have a control panel in front of you with a dial for each fundamental constant: the gravitational constant, the strong force, the cosmological constant, the fine structure constant. A dozen dials in total. You spin them at random. What are the odds that you land on a combination that produces stars? That those stars produce carbon? That the carbon ends up in planets? That the planets develop chemistry complex enough to self-replicate? That self-replication eventually produces something that can look back at the control panel and wonder who built it. The physicist Lee Smolin estimated the probability of a universe like ours emerging from random constant values at something on the order of 1 in 10 to the 229. This isn't a casual estimate. It comes from detailed modeling of stellar physics and the parameter space of possible universes. 10 to the 229. There is no analogy that makes this number graspable. Here is the most honest attempt. If you assigned 1 0 to every subatomic particle in the observable universe, not every atom, every particle, and then assigned another 0 to every particle in a billion copies of the observable universe, you still would not have written out all the zeros in that number. The universe you live in is an event of probability so small that the word unlikely fails entirely. One of two things must be true. Either there is something about the constants, some deeper principle, some equation we haven't found, that made them have to be what they are. Or there are so many universes, each with different constants, that configurations like ours were statistically inevitable somewhere. The first answer implies a hidden order to reality that physics hasn't uncovered yet. The second implies a structure so vast that the entire observable universe, everything you have ever seen, imagined, or measured, is a single data point in an infinite distribution. Neither has been proven. Both are taken seriously by serious physicists, and both, if you sit with them, are extraordinary. So why are the constants what they are? The most technically defensible answer begins with what's called the anthropic principle. The term was introduced by the British-Australian physicist Brandon Carter in 1974, and it comes in two forms that mean very different things. The weak anthropic principle says something almost obvious. We can only observe a universe that is compatible with our existence. If the constants didn't permit complexity, there would be no observers to measure them. So whatever values we find when we look, they will necessarily be life-permitting. Not because the universe was designed for us, but because we are a selection effect. You couldn't have been born in a universe without stars. So you weren't. And from inside your universe, looking out at the constants, everything looks arranged in your favor. Because only arrangements that allowed you to exist ever produced someone capable of noticing. It's logically airtight, and it explains, in a technical sense, why we shouldn't be surprised to find ourselves in a life-permitting universe. What it doesn't explain is why such a universe exists at all. The strong anthropic principle goes further, and into far more contested territory. It proposes, in various formulations, that the universe must have the properties that allow for conscious observation. Some versions of this are effectively philosophical claims about necessity and causation. Others merge with ideas from quantum mechanics about the role of observers in collapsing physical states. None of them are mainstream. Most physicists treat the strong anthropic principle as a category of speculation rather than science. But the weak version, the observer selection argument, led somewhere concrete. In 1987, the physicist Steven Weinberg used anthropic reasoning to make a specific, testable prediction. He was thinking about the cosmological constant, the same number we began with. He knew that if the cosmological constant were too large and positive, the universe would have expanded so quickly after the Big Bang that matter would never have clumped into galaxies. Galaxies require a certain amount of time and gravitational density to form. A large cosmological constant removes both. So Weinberg reasoned, whatever the cosmological constant is, it can't be so large that galaxies, and therefore stars and therefore observers, couldn't form. He calculated an upper bound from first principles. In 1998, 11 years later, two independent teams of astronomers studying distant supernovae discovered that the expansion of the universe was accelerating. This implied a non-zero cosmological constant, a repulsive energy in empty space driving the universe apart. When they measured it, the value sat just below Weinberg's predicted limit. Anthropic reasoning, reasoning from the necessity of observers, had predicted a physical quantity before it was measured. And it was correct. This does not prove the multiverse. It doesn't prove the strong anthropic principle. It doesn't prove anything about design or intent. But it demonstrated that the logic of observer selection does real work in physics. That you can derive constraints on physical quantities by asking, what values allow someone to be here asking questions? That is not a trivial result. It is the kind of result that forces physicists who would rather ignore these questions to take them seriously. And it opened a door to the most expansive and most contested idea in modern cosmology. If the fine-tuning problem is real, the multiverse is the most popular proposed solution. The argument is straightforward. If there are vast numbers of universes, each with different values for the physical constants, each exploring a different region of the possible parameter space, then the improbability dissolves. In a large enough ensemble, combinations like ours are inevitable. We find ourselves in a life-permitting universe for the same reason you find yourself on a planet with liquid water, because those are the conditions that produced you. There's no mystery. There's just a large enough sample to make the outcome expected. Leonard Susskind, one of the founders of string theory, became one of the most prominent advocates of this picture. String theory, he argued, naturally produces what he called the landscape, a space of perhaps 10 to the 500 possible vacuum configurations, each corresponding to a different set of effective physical laws. Eternal inflation, the idea that the rapid expansion driving our universe may have spawned countless others, each a separate bubble in an ever-growing cosmic foam, provides the mechanism. The landscape provides the variety, and the anthropic principle provides the selection rule for which bubble we find ourselves in. It is, on its face, a complete solution. And the physicist Paul Davies thinks that is precisely the problem. Davies, one of the most careful thinkers working at the intersection of physics and philosophy, has written extensively about why the multiverse is not as clean a solution as it appears. His concern isn't religious. It's about what counts as an explanation. A scientific theory, Davies argues, must, in principle, be falsifiable. It must make predictions that could, at least in principle, turn out to be wrong. The multiverse, as currently formulated, predicts essentially everything, because in a large enough ensemble, every possible universe exists. But a theory that allows all outcomes explains none of them. If your theory predicts everything, it has no power to distinguish between what should happen and what shouldn't. The multiverse, in this sense, doesn't explain fine-tuning. It restates it. The question moves from why do our constants have these values to why does the ensemble allow life-permitting constants to exist at all? The mystery doesn't disappear. It shifts one level deeper. This debate between those who find the multiverse explanatorily satisfying and those who find it a sophisticated non-answer is ongoing. In journals, at conferences, between Nobel laureates, it has not been resolved. Let's be precise about what remains unknown. First, are the constants actually constant? We assume so, but some theories allow for constants that evolved in the very early universe, values that were set during phase transitions, the way water locks into ice. If that's true, why are the constants what they are becomes a question about early universe physics we can, in principle, discover. We haven't discovered it yet. Second, is the fine-tuning real, or is it an artifact of how we choose to parameterize the physics? Some physicists argue that In different variable choices, the apparent precision looks less extreme. The tuning may be real, but the severity of it partly depends on how you frame the question. This objection hasn't been decisively resolved in either direction. Third, could life, or something like it, exist in a universe with very different constants? Our definition of life permitting is based entirely on carbon chemistry and liquid water. If complexity can emerge under radically different physical rules, then the corridor is wider than we think, and the coincidence less severe. We have a sample size of 1. Everything we know about life comes from a single planet, under a single set of physical laws. That is not enough data to draw firm conclusions. Here is what the measurements say. The universe has constants. Those constants sit in an extraordinarily narrow range. The margin for any of them to be different, while still producing something complex, is vanishingly thin. And no one, not the multiverse theorists, not the string theorists, not the philosophers, not the physicists working at the cutting edge of quantum gravity, has produced a fully satisfying explanation for why. You are the product of 13.8 billion years of physics operating inside that narrow corridor. Every constant held, every threshold cleared, every resonance landed exactly where it needed to. And from that chain of improbabilities, something emerged that can measure the constants, calculate the odds, and feel the weight of what those numbers mean. So here's the question this video leaves you with. If we one day find the deeper equation, the principle that explains why the constants are what they are, will that feel like understanding? Or will it just feel like the mystery moved,